Dear students, today we can begin a new chapter, chapter 12, Organic Chemistry, some basic concepts. In this chapter, we will study the nomenclature of organic compounds, isomerism in organic compounds, reaction mechanism, and finally, purification and characterization. So here we can see some basic concepts in organic chemistry. Berzelius, a Swedish chemist, proposed that a vital force was responsible for the formation of organic compounds. That is known by the name vital force theory. For the preparation of organic compounds, a particular force related to life that is required. That was the belief at that time. A vital force is required. That is known as vital force theory. Otherwise, it is not possible to prepare organic compounds. But it was rejected in 1828 when F. Waller synthesized an organic compound urea from an inorganic compound ammonium cyanate. Ammonium cyanate on simple heating, you will get urea. It is ammonium cyanate NH4CNO. On heating gives NH2CO NH2. That is urea. It is an organic compound, but that is prepared from ammonium cyanate in the laboratory. So the vital force theory rejected. It is possible to prepare organic compounds in the laboratory without the help of a force related to life. After that, after the discovery of urea, the next organic compound synthesized is acetic acid. It was by Kolb in 1845. Kolb's electrolysis, you will study it. After acetic acid, methane prepared by Barthelot in 1856. So all this proved that no vital force is required for the production of organic compound. It is possible to prepare organic compound in the laboratory. Now the different types of representation of organic compounds, complete, condensed, and bond-line structural formulas. It is complete formula. All the bonds in the organic compound is shown here. Ethane, CH3, 3 bonds with the hydrogen, CH, 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 single bond C, CH, CH, single bond H. It is the complete formula of ethane. Ethene, it is the complete formula of ethene. All the bonds are shown here. Ethyne, complete formula of ethane. You can see all the bonds. Methanol, CH3OH, CH, 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 OH. Or we can represent it in this way without showing the electron pair. HCHHOH. Here the electron pairs are shown. That is not compulsory. In complete formula, it is not compulsory to show the electron pairs. So without showing the electron pairs, it is represented here. It is complete formula of an organic compound. Now condensed formula. What is my condensed formula? Here you can see CH3, CH3. The bonds are not shown here. Condensed bond, ethene, only the double bond is shown. CH2 double bond, CH2. Ethyne, only the triple bond is shown. CH triple bond, CH. Methanol, CH3OH. No bond is shown here. It is known as the condensed formula. Now bond line formula. This compound CH3, CH2, CH, CH3, CH2, 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 CH3 can be represented in this way. CH2, CH2, CH, CH3, CH2, 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 CH3. The numbers are same. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And in bond line formula, we will represent it using only bond lines. No atoms are shown in this formula. So you take only the bond lines. It is the bond line. Only the bond lines, and that is represented here. Only the bond lines are taken. 1, 2, 3, 4, 5, 6, 7, 8. Terminals represent methyl group. All the terminals. Here there is a methyl group. Here there is a methyl group. Here there is a methyl group. As shown, it is here. One methyl group, another one, another one. And at this junction, here, what is present? A CH2 group is present. But here in this junction, a CH group is present. Why? Because three valencies of this carbon atoms are satisfied here with the three other carbon atoms. Only one valence is remaining, that is satisfied by hydrogen. So here a CH group, here CH2, 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 and here CH3. It is bond line representation. Cyclic compounds, we can represent cyclic compounds. It is the representation of cyclic compounds in bond line structure. We can represent in this way. Cyclopropyne. Actually, it is CH2, CH2, CH2. And in bond line structure, we can represent it like this. A triangle represents cyclopropyne. And cyclopentane, a pentagon represents cyclopentane. CH2, CH2, CH2. It is the bond line formula of cyclopentane. Cyclohexane. But it is chlorocyclohexane. One of the hydrogen atom is substituted by chlorine. So chlorocyclohexane. In that case, 6 carbon atoms are shown here in this hexagon and a side chain, chlorine. So it is chlorocyclohexane, bond line representation of cyclic compounds. Now you have a problem. For each of the following compounds, write a condensed formula and also their bond line formula. OH, CH2, 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 CH, CH3, CH, CH3, CH3. It is actually condensed formula, isn't it? Condensed formula and also the bond line formula. It is actually condensed. So it has a B part also. N triple bond C, CH, OH, single bond C, triple bond N. The condensed formula, OH, CH2 thrice, CH, CH3, CH, CH3 twice. A little more condensed. Here 2 CH2 group is there, 2, not 2, CH2, 1, 2, 3, 3 CH2 groups. Here all these 3 CH2 groups right together, CH2 thrice. CH, CH3, CH, CH3, CH3. That is written together here, CH3 twice. And see the bond line formula. OH group, you have to write OH there. And CH2, 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 sorry, CH2, CH2, CH2. Now CH, CH, CH3. Again CH, CH3, CH3. So only the bond lines are shown here. OH group is given because otherwise we will not understand which group is present here. If it is not written here, we will consider it as CH3. So surely OH group, you have to write OH group here. And the second case, C triple bond N, we can write it as Cn. CH, OH, Cn. So this CH is not shown here. OH, Cn, Cn. This bond line representation of the compound B. And you have to practice it. You'll get more examples from your textbook. Very simple to understand. Now, three-dimensional representation of an organic compound. Three-dimensional representation. CH4 is represented three-dimensionally. Here, this dotted line represents projected to the backside, projected to the backside, behind. That is the meaning. bond away from the observer, away from the observer. And that is known as dashed wedge. Now the solid wedge represent to the observer's side, bond towards observer, projected to the front. And here hydrogen, a bond, it is represented as usually a bond. It is in the plane, represent the plane. This hydrogen also in the same plane. So bonds in the plane of paper. These two represents bonds in the plane of paper. And this formula is known as wedge and dash formula, or wedge and dash representation of CH4. Okay, now classification of organic compounds. Organic compounds are mainly classified into two: alicyclic or open chain compounds, cyclic or closed chain or ring compounds. Cyclic compounds are again classified into alicyclic compounds and aromatic compounds. Alicyclic compounds are again classified into homocyclic or carbocyclic compounds and heterocyclic compounds. Heterocyclic compounds, non-aromatic. Aromatic compounds are classified into three: benzenoid compounds, non-benzenoid compounds, and heterocyclic aromatic compounds. Benzenoid, benzene, you know, C6H6. And if there is such a ring in a compound, that is aromatic, benzenoid aromatic compound. If there is no such a ring but aromatic in nature, that is known as non-benzenoid aromatic compound. And heterocyclic aromatic compounds, there will be another atom like nitrogen, oxygen, or sulfur in the ring. Instead of carbon, there will be nitrogen, oxygen, or sulfur. That is a heterocyclic compound. And alicyclic or open chain compounds, its classification we have studied. Open chain compounds are classified into saturated and unsaturated. Saturated, only one type, alkanes. Unsaturated, there are two types, alkenes and alkynes. It is a classification of organic compounds. Here you can see some examples for heterocyclic aromatic compounds. Furan, here instead of carbon atom, there is an oxygen atom. So it is heterocyclic. Here carbon, 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 and oxygen. All the atoms are not same. One is different. So heterocyclic. Furan, thiophene, instead of oxygen, here sulfur is present. Thiophene, carbon and sulfur. Here carbon and nitrogen, pyridine. Now homologous series. What is meant by homologous series? Alkanes, an example for homologous series. Alkene, another example for homologous series. So homologous series is a group of compounds. Homologous series is a group of compounds which has the following characteristics. They can be represented by a general molecular formula, and the adjacent members or successive members differ from each other in molecular formula by a CH2 group. Adjacent members differ in molecular formula by a CH2 group. They can be prepared by same methods and have similar chemical properties. So altogether we can identify four requirements for a homologous series. Homologous series is a group of compounds which has general molecular formula. And second, adjacent members differ by a CH2 group. They can be prepared by similar methods of preparation. They have similar chemical properties. They have similar chemical properties. That is homologous series. There are a number of homologous series of organic compounds. Some of these are alkanes, alkenes, alkynes, haloalkanes, alkanols, alkanals, alkanones, alkanoic acids, amines, etc. We'll see in detail about all these functional groups. Their nomenclature and such details we will discuss. You may have some idea also. Now the nomenclature of organic compounds. There is a trivial or common system of nomenclature. In that there is no a regular rule for the nomenclature. Just some names are given. Some examples, you can see some examples here. CH4, methane. CH3, CH2, CH2, CH3, normal butane. That is named as normal butane. CH3, twice CH3. That is named as isobutane. It is normal butane. What is the reason? 4 carbon atoms. So normal butane. Here also 4 carbon atoms, but one is branch. So it is named as isobutane. CH3 4 times C. Neopentane. That means one carbon atom is surrounded by 4 CH3 groups. That is known as neopentane. Total 5 carbon atoms, therefore the name pentane. Neopentane. CH3, CH2, CH2OH. This functional group an alcoholic group. So it is known as normal propyl alcohol, N-propyl alcohol. N-propyl alcohol. HCHO, formaldehyde. That is a common name. HCHO, formaldehyde. CH3 twice CO or CH3CO, CH3. CH3 twice CO means CH3, CO, CH3. That is acetone. CHCl3, chloroform. CH3COH, acetic acid. C6H6, benzene. C6H5OCH3, anisole. C6H5NH2, aniline. C6H5COCH3, acetophenone. CH3O, CH2, CH3, ethyl methyl ether. All these are some common names. Earlier, the organic compounds were given common names, but when we try to study the names of these compounds at different regions, the names were different, so the study was very difficult. So there is a requirement of a universally accepted nomenclature, and that was given by International Union of Pure and Applied Chemistry, and that is known as IUPAC nomenclature. The IUPAC system of nomenclature. First, we can see how to name alkanes. To name alkanes, first write word root. What is word root? One carbon atom, the word root. Alkanes containing 1 carbon atom, word root, meth. 2, eth. 3, prop. 4, but. 5, pent. 6, hex. 7, hept. 8, oct. 9, non. 10, duck. These are the word roots. For example, CH3, CH2, CH2, CH3. How many? 1, 2, 3, 4. But is the word root plus N, butane. CH3, CH2, 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 CH3. Word root 6 carbon atoms, so hex plus N, hexane. C9H20, 9 carbon atom, word root non, N, nonane. Now the branched chain alkanes, name and number of substituents in the alphabetical order plus word root plus N. First you have to find out the substituents. The chains, side chains are considered as substituents. So find out the substituents, name them, and count the number of side chains, and based on it you have to write the names of the substituents first plus word root plus N. An example. It is the compound CH3, CH, CH3, CH2, CH3, CH3, CH, CH2, CH3, CH2, CH, CH3, CH3. So here you can see it is a substituent. CH3 is a substituent. CH2, CH3 is another substituent. Again a CH3. So here there are 2 substituents, and the names of the substituents CH3, methyl, methyl. CH4 is methane. 1 hydrogen is substituted. Then it will change to CH3. So it is known as methyl, methyl. And CH3, CH2, ethyl. CH3, CH2, ethyl. Now what is next? You have to number the carbon atoms in such a way to get minimum number of the carbon atoms carrying the substituent. First number the carbon atom and then you have to name it in the alphabetical order. So here the substituent should get minimum number. If you start numbering from this side, it will get number 2, 3, 4, 5, 6. It will be 6, 7, 8. It will be 8, 9. So 2, 6, and 8. 2 plus 6, 8 plus 8, 16. The sum is 16. And if you start numbering from this side, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is 2 plus 4, 6, plus 8, 14. If you number from this side, the sum is 14. If you number from this side, the sum is 16. So which will be preferred? Numbering from this side. That is correct. So you have to number from this side. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 carbon atoms. And the substituents are present in second and 8 CH3. 2 methyl groups are present. Dimethyl. And in the fourth carbon atom, an ethyl group. Methyl and ethyl, which is alphabetically first. Ethyl is alphabetically first. So what is the name? 4-ethyl 2,8-dimethyl nonane. Nonane. 4-ethyl 2,8-dimethyl nonane. That is the name of the compound. Okay, I'm stopping here. You have to try to name more number of alkanes having side chains or substituents. Make it thorough. It is only an introductory class. After making it clear, we can discuss the remaining nomenclature in the next class. Okay.